Well, I've recorded this one probably two or three times for whatever reason, and each time I kind of miss something, or no, I don't know, I usually just miss something. Um, Hopefully we nail it this time. This is going to be a lot less about the rolling codes and the car and that reverse engineering side. This is more going to be about .subfile analysis and how to say you've captured a signal and you want to know like a signal that's not a supported protocol, and you sort of want to know a little bit more about it. Maybe even attempt to analyze it and see if it's a rolling protocol or not, or see if you can predict it, or see if you can change a few things around and sort of just see what happens. Just generally play around with stuff. And also, maybe you might want to clean up a signal and remove some of the noise from before and after the signal, or maybe you want to clean up the actual signal itself and get it nice and sharp. Maybe the receiver's having a bit of trouble picking it up or something like that. Sort of just any manner of things you'd want to do. Perhaps you've got a signal recorded from a software-defined radio, and you got all your demodulated bits, and you want to put that into a .sub file and transmit that with a flipper. This would show you how to do that also. So there's um, all the base knowledge that I'm about to push into this video, condense into this video, is going to really give you the ability to just do whatever it might be that you'd want to do. You have the ability to. I mean, the limit is your imagination, really. Um, so I'll obviously start. I'm not going to use the software defined radio at all. This is just solely going to be the flipper. So we're going to be using the flipper to get our information and do all of our cleanup and all of that stuff. So I'm just going to go into where are we? Here we are. Into some gigahertz naturally. I'm going to go into not read raw. Sorry, I'm going to start with read actually, and I've got my modulation and my frequency set. I'm not going to go too much in on that. I've covered that I think a few times already. Um, I know that this is the frequency I need to be using for my particular fob. And I've also gone and put bin raw to on. This is not a supported protocol, so when I press the button, nothing will come up unless bin raw is active, and then it will capture bin raw. Um, there we are. And that bin raw is just binary raw. It's just raw binary data of whatever was received. The bin raws are actually a really good tool. That's why I just want to cover these as well. They usually get very nice, um, clean signals from a bin raw when you utilize them correctly. They're quite powerful. Um, so here I see I've got about these 500 odd bits. Got a couple of zeros here, so just some non-transmission. A handful of C, and then that's kind of it. There's usually going to be a little bit more than that. If you open the .sub file, you'll actually see it. But unfortunately, you can't like press down or anything and go through the um, what's on the display is all you get to see, which is a bit unfortunate. Then this TE, this time unit here of 751 microsecond. Now the way this time unit here works is this 750 microseconds is applied to every bit that was captured in this file, or every sort of symbol. Um, so this first byte here, this 00, this would be about 8 zeros, and eight each of those A are for the duration of 750 microseconds. So that would be 750 microseconds times 8 would give us, I don't know, something. I suppose we can whip out the old calculator. So we've got 750 microseconds times 8 would give us 6,000 microseconds there. And then we get into C, and that would be, so this is, obviously they're zeros, so that means they're low. So that'd be 600 microseconds low, or of no transmission. And then we get to C, which is 1100, so that would go high for two 750s, so that's 1100. So we get 750 times 2, which would give us that 1500 microseconds of high. And then it would go low for 00, which would be 1500 microseconds low. And that appears to continue over and over and over and over again. So I'm just going to capture a couple more bin raws because it's good to capture more than one to just be sure that your data is coming through and you're capturing what it is you want to capture. So I'll pick that again. And now I see a bunch of nines. I still see around that 750. I'm still seeing around that same 500 bit. So it looks like my signal. This kind of does look like I've captured what I wanted to capture, but the data is significantly different. So I'm just going to go over why that actually is. So what we've got, I think we can find that, here we are, is we've got that bunch of nines, we've got a bunch of C. So if we actually go into the old text document here, and I type out C 1100, or I might zoom in a little bit now, can't hours away. 1100, 1100, 1100, 1100, and then I do the same for 9, 1001, 1001, 1001, 1001, 1001. If I remove the spaces here, like so, and that might even appear. What we see when I just change the alignment a little bit, if I just line up these zeros here, well, all of a sudden the data is identical, completely identical. We can keep going with here, keep going with C, 0, keep going with 9, that'd be 1, 0, 0. As you can see, then obviously another 1, but C also starts with 1, 1. So what that is it's just our alignment was different. This bin raw happened to catch, say, this first bit here, and this second one, this second bin raw, looks like it captured. So the C captured the first one here, and this 9 looks like it started its capture from this one. So the alignment was just a little bit off. You'll get the same thing with I believe 6 will do the same thing. 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, which is 6. And as you can see, we set the alignment. Data's the same. And 3 will do the same thing, which is 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. 0, 0, 1, 1. Ah, look at that, I've actually aligned C2, 3. And that's in this example. So you can see they're always, even though the data does appear to be completely different, it's good to just keep, sort of double check it against, these alignments. So yeah, C, 9, 6, and 3 over and over again will sort of give you, if you align them, will give you the same data there. So both of these captures are probably will contain, whether it's offset or not, will actually contain the information correctly. We can tell that because we've got around about the same amount of bits. It's just this one caught on a little bit later than the first one, and this TE delta is also around about the same as well. It likes to land on these nice round numbers. So not land. Oh, that's something. I think that's not even my key. Wonder what that is. What was I just saying? So So gigahertz protocols like to use really sort of round numbers, like sort of uh, 25s, 50s, 75s, and hundreds. They like to use those sort of those nice round numbers. This 40 isn't. I mean, you could say 740 is a round number, but it's not as common as something like 750 or 100 or um, 200 or 150, like sort of nice big round numbers. So it's probably safe to say that this 750 is most likely quite accurate. That 750 would be the number we're chasing here. The flipper's not going to be perfect every single time. A software-defined radio will nail it, but the flipper's going to be a bit hit and miss. So you've got to kind of work out, guesstimate and sort of average out. So this one's 745. So you can see it's really floating around 750. We've got all those C's again as well, which is another indication that we're hitting what we're supposed to be hitting, because there's the C's. Um, here's the C's again. It looks like we've caught on a little bit later this time. This one's got a bit of non-transmission in it. This one's got a bit of transmission in it, and then you hit what appears to be some data. Well, it looks like what we have here is a preamble, and then we get into data, which is what you often see with radio protocols is a preamble and then some data. So I might capture a few more if I can get my bloody recognise it. Oh, here we go. There's that 6 again. So still the same. 500, 600 bits. It's still relatively relatively in the same ballpark. So yeah, I'm pretty confident we've hit our signal here. Definitely. This 750. We've got it's 6 aligns with everything we've seen so far. I've got a bit of data here. Looks like a preamble. Bits are around about the same. It looks like we're on the money here. So I'm gonna save this one. I'll just save it. I'm gonna flip it here. So save. I'm gonna name that now bin raw 1. Just gonna save that. Now I should be able to just back out and where do I want to go here? So find some gigahertz here, and then we're gonna find that bin raw signal. There it is. And download that. On the desktop. It should pop up here, and here we are. So now let's pull apart, have a look at this bin raw file and see what we see. So open that up, and right away we have all those 6s that we saw, and then we've got to do a bit of data, and we can see a lot more of that data now because we don't have to worry about the confines of the display. And then we've got a bunch of zeros at the end there, so it looks like that's where the transmission ended. You see our frequency information at 43392. We can change that to whatever it is that we want. We can go to 43388, and we can save that back to the flipper and transmit on 43388 if we wanted to. This is our modulation preset. We're using the AM650, the on-off keying 650. We can change that to the 270 if we wanted, or we could change that to the frequency shift keying. I think I have a FM signal here, for example. We can change it to this, and that would change it to FM. You can also do custom modulations as well, but I'm not going to dive deeply into. I'm not really going to dive into that at all. Derek Jameson has great information and a really good video on custom modulations and on how to actually to do that. So I'll leave that one to him, I guess. We have this latitude longitude thing, which I'm assuming is if you've got a GPS module attached for war driving or something. I'm guessing. Protocol. Now, protocol is a binary raw, the bin raw protocol, which just takes the raw binary and spits it out essentially. the bin raws are really good at sort of locking onto data and find and excluding it from the noise and all that. So that's why it's quite a strong something I want to go over because they're a really strong tool. Um, we see here this is our TE, that time unit there. So each bit is represented. So each high and low, or each sort of bit, you really, so say what have we got here? 6 is 0110, and then 0110 again. Oops, 750 here would be 750 low, and then it would be 750 high, and then it would be another 750 high, 750 low, another 750 low, 750 high, 750 high, and 750 low. So that's in microseconds. So 750 microseconds high, 750 microseconds high, wait, 750 microseconds low, 750 microseconds high, and then high again for the same duration, then low for that duration, low again for that duration, so on and so forth. That's how that how that works there. Um, we've got here these bits and bit raw. We notice they're the same value. So you might be wondering why I have the same value twice, and it took me forever to wrap my head around why I have the same value twice. And that's actually because um, sometimes bin raw will give you two signals, or you can put two signals in the same file. They don't have to be the same information. They could be whatever information you want them to be. But you have to have this bit raw is for the amount of bits that is in the segment, and then this just bit is for the amount of bits that are in the entire file. So I would have to actually, in this case, I would have to double this. So 471 times 2, 471 times 2 would give us that 946. This would have to be 946. Wait, I didn't even know. 946. That would have to be 946. Obviously, if I removed a ton from there, now we've only got 8 bits here. Well, then I have to put this one has 8 bits, and this one has what is it that plus 8, so that'd be 470. Yeah, well, 479 bits all up in the entire file. So what have I done there? So that's how that works there. And you can obviously go and do stuff like I want to keep this data here. You can make up your own data as well. So for example, you wanted to transmit 100101101 or something like that. For instance, how many bits is that? Actually, it doesn't matter how many bits it is. Well, that's 10 bits there. So we can put 10 bits. So now we're at 81 here. 81. And then we've got so that's 4 bits, and this would just be 00 in this case. So oh my god, I'm not sure if we actually count that here or not. I'm not sure we do. I have to do a little bit of experimenting and see. But what's this? This is CB4. Yeah, so we've got CB4. Oh, hang on a minute. CB4. Oh, come on, G4. And we're going to do it in bytes, so we're going to add that other 0 there. And that's our 10 bits. I've got all the bits in the entire protocol, and then that's how many protocol in the entire file, and then this is how many bits are in each segment. All right, well, let's let's fix that back up to where it was. Control like that. We can also, if we wanted the signal to transmit a little bit closer to what it should be, we would change this 49 to that 50. And that would sort of clean that up. We could maybe even remove a handful of the zeros. We could add more sixes or reduce the sixes if we wanted to extend the preamble or something. So there's a little bit you can do. We could change some of the data fields as well and transmit different information. But in order to sort of start changing data, you really need to work out what data you're changing and what data what the data actually is. So that's what we're gonna go and do now. So I've got our just pulled just the data from the binaural file, and we're gonna sort of just pull it apart and show you how you can pull that information apart and look at your signal. Look at the signal. So these 6 6s, I'm just gonna turn these into 6 6 in binary. Replace all. Um, and then these zeros, return of what's that, 8 zeros, 1, 2, 3, 4, 5, 6, 7, 8. Copy that. Control B, B, B. The reason I didn't do the Control H thing for these ones is it's actually going to nick these 2 zeros and change them as well. It can get a bit obnoxious. I should have done the zeros first. Here we are. And then here we go with our data field here now. So I'm just going to sort of have to do that by hand. 0, 1, 1. Oh, what the heck? So what's that? That's 6 9 is 0 1 1 0 1 0 0 1. A6 is 1 0 1 0 0 1 1 0. 5 6 is 0 1 0 1 0 1 1 0. 5 6 0 1 0 1 0 1 1 0. 6A 0 1 1 0 1 0 1 0. 5A is 0 1 0 1 1 0 1 0. 5 5 is 0 1 0 1 0 1 0 1. 5A is 0 1 0 1 1 0 1 0. 6 5 0 1 1 0 0 1 0 1. 5 5 is 0 1 0 1 0 1 0 1. 6 9 0 1 1 0 1 0 0 1. 8 5 1 0 1 0 0 1 0 1. Yeah, let's go. 6 5 0 1 1 0 0 1 0 1. 6 9 0 1 1 0 1 0 0 1. And this is 9 0, so 1 0 0 1 0 0 0 0. There we go. And now it's pulled our data from hexadecimal into straight binary. So I'm going to remove all the spaces out of that. That's all. And there we go. We have our demodulated our entire transmission in its demodulated bits or its symbols. It's not really, you shouldn't really think of this so much as the as the bits or as the sort of information or whatever, uh, data, whatever. It's still encoded. So what these really are our lows and our highs. So we have a low for a single duration and a high for 2 durations. A low for a single duration and a high for 2 durations is really shouldn't be thought of as the actual bits yet. These are just the demodulated symbols, highs and lows. To get our bits out, our logic bits out, we have to check the encoding. We have to decode them, and this isn't is an encryption, so to speak. This is a way of of information being transmitted and received, um, in such a way that information isn't lost, or um, computers can sort of correct errors and things like that. They use different encoding schemes to safely transmit that data without getting it muddled, or without losing it, or whatever they bloody do. Um, so I've got a handful of different kinds of encodings. There's, you could just have, so for example, say we have sent the information 5 in hexadecimal. So that would be in 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 clear encoding, it would just be 5. So each bit here would represent a logic bit in this case. So this would just be sort of like in the clear encoding. Then there's another style of encoding called Manchester encoding, where is each logic bit is represented by two symbols. So for a 0, it would be 0, 1. For 1, it would be 1, 0. And then for 5, it would be 0, 1, 1, 0, like that. And this would be 5 in Manchester encoding. So we're using two symbols to represent one logic bit. So that represents a 0, that represents a 1, that represents a 0, that represents a 1. In this case, each one just simply represents itself. Then there's some sort of PPM encoding, uses something like like this for a 0 bit. I think it's 100. No, yeah, 1000. And then for a 1 bit, it would be 1110. So it's sort of like a pulse, um, sort of like a pulse width sort of thing, where we have a short high and a long low represents a 0, and a long high and a short low would represent a 1. So for 5, we would have another short high, long low for a 0 bit, and then for the 1 bit, we would have a long high and a short low for that long bit, for that 1 bit. And then there's I think Keylock uses pulse width modulation. I'm pretty sure Keylock is like 110, 100 for a this for a 1, this for a 0. So 5 would be a 0 here, 100, and then we'll have a 1 over here for 10 for 5. And I'm pretty sure this is how, so it's 0, 1, 0, 1. So we can see this is using, just in the clear, each bit represents itself. Manchester encoding is using 2 bits. This pulse width modulation is using 3 bits to encode a single logic bit. This is using 4 bits to encode a logic bit. There are other encodings that may use, say, this for a 0 and this for a 1. So now there are different amounts of bits per, so it doesn't always stay the same. It can be a bit kind of a bit arbitrary, and depending on the data, it would even change how long the signal is. Can't remember what kind of encoding this is, but it's kind of like a pulse width modulation as well, I guess. So yeah, this would be a 0, this would be a 1, this would be a 0, this would be a 1. It could even be the other way around, where um, this is a 0 and then this is a 1. Could be all kinds of things. You could have, well, maybe this could be a 1 and this could be a 0. Just all kinds of different styles. And actually, this would just be clear encoding because the timings would be different, wouldn't they? But there are all kinds of different coding. So you just have to look at your signal and just try and find. Usually, you'll find um, two different things happening. So you'll either have this or this happening, or so there'll be two different states or something like that, so to speak, to represent each one or a zero. So I guess we need to work out exactly what we have here. What kind of encoding this is. And one of the best ways to work out what kind of encoding you have is to just check if it's Manchester. There's also other styles of Manchester, by the way, and same with these. These could be inverted. So, for example, in Manchester, you could have 1 0 would represent a zero, um, and 0 1 would represent a one. You could also have sort of an inverted um, kind of modulation where one means a zero and zero means a one. So this would be like this inverted. So that can happen as well. There's all kinds of different things you can do. This is the most common style of Manchester encoding, and Manchester encoding is also incredibly common. So one of the first things you can do is to just check if you have Manchester encoding or not. And the fastest way to check if you have Manchester encoding or not is to look and see how many bits in a row you have. And the most amount of bits we have in a row, I know we've got like a ton of zeros here, but that's the end of the transmission, so we're not going to pay attention to that. But the most we get in a row seems to be two. We either get 2 1s or 2 zeros. We never get 3 1s or 3 zeros. And the reason you never see that in Manchester encoding is because you either have a 1 0 or a 0 1. So the most that could ever be next to each other are 2 zeros. So if you've got 0 1 and then 0 1 again, well, it's just going to alternate. But if you flip that 0 1 and 1 0, the most you're going to have next to each other are 2. And then, so that's the first thing you can do to check if you have Manchester encoding. And so far it looks like we do. And then the next thing you can do, obviously, is to find a Manchester pair. And then just, so what, a 1 0 or a 0 1. You don't want to start on the 0 0 because that's not a valid Manchester pair. You either have a 0 1 or a 1 0. So you want to grab a 0 1 and a 1 0 and sort of step through it and have a look and see. So what's that? 1, 2, 3 bits, 4 bits, 5 bits, 6 bits. So far it's looking good. Sometimes you can kind of fall off alignment. So for example, here's a 0 1. It looks like we're all in alignment. And then 0 0. That's not a valid Manchester pair. So if you're doing that, just check again by changing your alignment. So instead of coming from this 0 and checking the Manchester data that's failed, we can start from the 1 and just have another look. And if this also fails, then you can be pretty confident that you don't have Manchester encoding, but this looks like it's not failing. This is a good indication that we've got Manchester encoded data here. Right, so based on that, I like to have multiple copies of my data in case I mess something up, so I'll throw this over here, and what did I say, we were lined from here before, with correct me, yep, so all these zeros, I'll just kind of get rid of these, I guess. We don't really need them. What just happened there? Now we need to pull out our preamble from our, or even discover if we have a preamble in this. Obviously we've got, repeating data over and over and over and over and over again. So let's try and find a spot where that stops happening, where that breaks down. The best way to do it is to start in the Manchester pair, and then instead of looking at the whole 6 or whatever, because we could be misaligned somewhere here. You want to align yourself to the Manchester pair. So just sort of check from the front if we're still good on the Manchester pairs here. Yeah, we're aligned correctly. And then sort of just start separating each pair out and look for a point where the pattern stops happening. So it looks like we're going from 0 to 1, 0, 1, 0, 1, 0, 1. That's 0. So we want to look for a point where that pattern breaks, where that stops happening. So instead of going through all of it here, I'm just going to pick an arbitrary spot around, I don't know, around here or so. Um, and just start from down here, because all this is, let's check it. Yeah, that's still all preamble there. Just to make it a little bit quicker, 0, 1. So 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1. We expected a 0 again, we got a 1. So that looks like right there, that looks like the start of our data. So I'm going to grab this. I'm going to grab that data, separated from our preamble now. You won't always have a preamble, so the best way to the best thing you can do is to capture a few signals and do this to a couple of them, and then compare your results, and then you'll start to see static portions, non-static portions. You'll see if it's rolling, you see if it isn't, etc. Then you can look at your encodings, at what encoding it's using, and really start to tear it apart. Luckily here, we sort of worked out pretty quickly that I had a preamble. We know it's Manchester. So what now? We have to de-Manchester this data and get our logic bits out. So that's just the way that works is 1001, 1001 is 10 is represents 1, 01 represents 0. So you can literally just get rid of the bit at the end, and that will be the data. So in this example, we have A or 10 in decimal. So to do that, we just remove every end one, like every sort of second bit. So I can just go through it like this quite easily and decode the data from Manchester into its logic bits. There we are. Another good thing to look at after you've done that is you've got that 56 bits here, which is 4 goes into. So usually these protocols will use 4 bits, maybe 4, 8, 16, 32, sort of stuff like that, or it might even be a little bit offset like this one was with 56. But it's a 4 always goes into it most of the time. I have seen some that are 33-bit and things like that, so that's something to look out for. But you capture a ton of signals and sort of look at them all together, and you sort of start to see a bit of whether or not you should have a certain amount of bits or not. Right, we can turn this into hex now. So we've got broken it down into the logic bits and the actual data of the protocol, as opposed to it's encoded. It's encoding, and we can now begin to actually decode the message or the data. So that's B4 5 C O D O 1. That's B again. That's 1 1 and A. There, like that. And if anyone's been following some of my previous videos, will notice right away that this happens to be my key. So we've actually decoded the data here correctly. So that bin raw did in fact have legitimate data in it, and we have managed to extract that data. So now if we wanted to, we could say change the data. For example, we could turn this A into a 5, and then we'd have to turn this into 5. and then we have to turn it back into Manchester encoding back here. So for example, I only just changed the end, so this is still Manchester encoded here, so I'll just how many bits is that? 8 bits. Just turn this part back into 5, 0, 1, 0, 1, 0, 1, 0. No, that's not correct. 0, 1, 1, 0, 0, 1, 1, 0. No, so we'll just staple that back on at the end there. And then we can stick all the data back together. Like so. And then we need to separate it back out into bytes. That's every 8. Oops. Oh my goodness. Write that back out into bytes. I kind of don't have all the zeros there, but that's fine. We'll just hold on to them. To give that the rest of its byte. There we go. Which is just no information, zeros. Yeah, that's correct. And now we can turn that back into hex. So what's that? That's 6 there. Replace all. And then we'll sort of go through these as well. So that's 6 9. So that's 6 9. That's A6. That there is 5 6. That's also 5 6. That's 6A. That's 5A. That's 5 5. That's 5A as well. That's 6 5. And the reason we're seeing 6 5A, etc. like that is just sort of a byproduct of Manchester encoding, because we only ever get a 1 0 and a 0 1. So we can only have a handful of different values up here. So if you sort of do get something like this in your signal, it's sort of these 6 5s, A's, etc. and 9s will appear. So it's a good indication that you might have Manchester. What is this? This 5 5. This is 6 9. This is A 5. Oh my god. A 5. This is 6 5. That's 6 6, right? Yep. And this is 6 0. Right, so we'll grab that. Copy it. And we'll take that back to our bin raw sub, and I'll make sure I just keep those zeros, so I'll do it from here to make sure the bits are all the amount of bits are the same. So control B. Yep, there we go. And there we go. So we changed some information, and now we can save that and send it back out, or we could make a new .sub file and sort of control Z. So we've got the old one here, and now a new one we could file save as, um, bin raw 2 dot sub. Make sure you change it to all files, otherwise it'll be called .sub.txt, and that would be really annoying. And you can save that, and then throw this bin raw 2 onto the flipper and transmit that. You can also um, invent whatever data it is that you want here instead. So, for example, say you wanted to send hello or something, and you wanted to encode that information in ASCII. So ASCII uses like 8 bits to represent. Crack up, that was 8. It actually was 8. 8 bits to represent a single letter. This probably isn't H in ASCII. This probably isn't anything in ASCII, to be quite honest. But I'm just going to type some random binary here and just pretend that that's what it is. I don't know, put a 0 here. And just pretend that's what it is. And then we can then turn this um, into hex. So what's this? This is C6. C6. This is 2E. 2E. This is actually too many bits there. This is oh, actually, you know what? Forget that it's too many bits. Let's just keep it. So this is 3 9. 3 9. This is that's 8. That's so well, we'll make that 8 as well. I guess just by adding zeros to the end. That's A. That's 8. Obviously we want to put them in bytes, so there's no information at the end of that as well. So what we actually wound up having here is 1, 1, 2, 3, 1, 2, 3, 4, and that wound up just being 8 and 0. And then we can put that here, and then what's this? This is 8, 16, 32, 32 plus 4, I guess. 32, what's that? 36. So we put those 36 bits all up. 36 bits in the segment, and obviously in the whole file there's also only 36 bits. We can change our TE value from 750 to say 100. So now for this C 1100, we've now got it's high for 100, then it's high for another 100, and then it goes low for 100, and then low for another 100. And that's sort of what that would transmit. So you can you change your frequency and your frequency modulation. You change your frequency here, and you can transmit whatever information it is that you want. And you're able to, as we saw, we were able to alter some of this information and retransmit that out, or we're able to invent information and transmit that out, or so we can do whatever it is that we want to do with it. We can even come back to our bin raw and remove a bunch of these zeros if we want to, just to make it that way we can transmit it back to back a lot faster. Maybe our protocol doesn't really need all of these sixes, maybe it only needs say half of them or something, so maybe we can transmit even faster again, and we just have to alter the amount of bits that we now have. There's all kinds of possibilities that you can do once you understand how a bin raw file is set up and how it actually works. So now we'll move on to the actual read raw, the raw.sub files, because I'm sure file rule here is for that one. So I'll pull up the flipper again. Where's my mouse? There it is. Go back, where am I? Back here, clicking that. So gigahertz, you've got your raw, same frequency and modulation, etc. It's going to hit record. Grab my button and press it 1, 2, 3, 4, 5 times. Hit stop. And then I'm just going to save that as raw 1. And go back. The SD card, sub gigahertz, and find that raw file. There it is. Download that. There we go, there's our raw file. Right, the one that you're all here for, I reckon. We'll open up that and we just see a bunch of random ass information in here. What the raw file does is it just gives you everything that was received. It's got all the information there. The bin raw files like to find the signal, they scope it out, and they latch onto it and they give you that information back. So if you can find it, it gives it back to you quite really clean. These raw files just give you back. They don't do any interpretation. They don't do any guessing. They just give you back whatever whatever was sent or whatever was received is what it gives you. So whatever's floating in the air is what is captured. Same sort of setup. You've got your frequency, you can change that. You've got your modulation stuff, you can do the same thing. This says protocol raw as opposed to bin raw because this was just a raw capture. And then we've just got our raw data, just our straight raw data. And there it is. Right, so how do we know what part of this is even the signal, or what on earth is even going on here? We've just got numbers all over the bloody place, and nothing makes any damn sense in here whatsoever. Where's my vape? Thank you. Well, the first thing we can do to try and find out what's going on is literally, let zoom out a little bit, is literally just to look at it. The first step of analysing is literally just looking at it. So as we scroll through, we see this pocket here, a very uniform kind of, everything's like very, this is all sporadic and this is very uniform. And this being uniform is a bit of a byproduct of all the values being identical. And when they're identical, we've sort of got a bit of that time unit kind of thing happening here, right? That's going to be our data. As we scroll through, we see it here again. So we've got it once, we've got it twice. Keep going. Here it is 3 times. There it is a 4th time. Here it is a 5th time. And that looks like that's it. And we only captured, well, as we saw, we only captured 5 signals, and we've just found 5 of these little pockets. So it's a pretty good indication that that's our data, and that well, it is. So I'm just going to grab all of that. Pressing every button under the sun that I don't want to press. So I'm just going to grab all of that, copy that, and throw it over here. As we scroll through it, you can see we've got that raw data keeps popping up again and again. I think it just captures a certain amount and then it just prints raw data again. It doesn't look for the beginning of an end of a signal and just print raw data when it sees another signal. It just prints raw data just randomly. As you can see, we've got these values here and then they're here as well. So this is like halfway through a signal, it's decided to print this raw data. So I'm just going to get rid of that. and just look at the data. Um, now, right, so now we've just got the data left. Gonna make another thing, so if I mess up, I've got my original data. And now we can sort of start pulling this apart. So I think first off we want to kind of isolate our signal, right? We've got a bunch of what appears to be noise, and then we've got our signal. So let's try and find the beginning of our signal here. We've got all these 1500s. It looks like around here somewhere. So it's always good to grab a little bit more noise than to not. Um, so you'd rather grab noise than to sort of delete some of your signal. So um, it's it, so if you can just grab a couple of bits of noise, and sort of go that way. Um, that way you don't accidentally delete some of your data. Now we need to find the end of this first signal here. So a bunch of 15s, bunch of 15s, bunch of 15s, and now it goes to 7. But as we can see, actually I'll have the control Z here. As we can see, when it comes into these 7s, it's kind of 7, 7, 7, 7. So that's kind of, yeah, there's another 15, 7, 7, 7. It's still pretty uniform, whereas this is like 100, 100, 400, 100, 200, 37,000. Very random. Um, so this is something we're going to actually have to pay attention to, and I'm going to explain a little bit here. Um, oh well, obviously, if we think back to our bin raw files as well, we're seeing those 750s as our unit, and we know that these 1500s would be 2 units. As 750 times 2 is 1450, but I'll sort of come down here anyway and showcase this. So we're seeing we've got 1500, and that looks to be our time unit. And then, you know, as we were looking through the signal, we spotted 750. So this is a good indication, because this is half of this number, that our time unit is actually this 750. If we had have seen something like 3000 pop up, well then we would go, yeah, that 1500 is just our time unit there. That's a singular symbol, or that single bit sort of thing. And this would be 2 of those. You're not always going to get 1 or 2. You can also get 3 or 4 or 8 or something, for example. So let's start with, say, 100 as our time unit. We can see something like 200, we could see 300, or 300, we could see 400, we could even see 4,000. Um, that just means that the single um, what am I trying to say, man? We could even see all the way up to like 4,000. That would just be 100. What's that? 40 times, and this would be 104 times, 103 times, 102 times. So that's something to sort of be a little bit aware of. You know, you're not always looking for just 100 and say 200. Also, keep your eyes peeled for the other variations of that original time unit. So you know, your 300s or your 400s, because they can still possibly exist. You won't always just have 2 units. You could have 3 or 4 or more different units. And obviously with that 1500, you know, we saw one that instead of going up like we would expect, it went down. So you could originally see something like 3000, thinking that's your time unit, and then all of a sudden see a bunch of, and then all of a sudden see something like a 500, for example, and that would turn our 3000 into how many units would that be? That would be 6 units. So the 500 would just be, say, 1, and 3000 would be 1, 2, 3, 4, 5, 6 ones. So that's something to certainly keep in mind. So I'll come back here to our data here. We've sort of separated out so 200, we've got a little bit of noise. Yeah, that's fine. We'll come down to the end here. So we're seeing these 700s. So now instead of thinking of these as our singular units, we now know that, hang on a minute, this is our singular unit here. So we want to keep these 700s. And there's some 1500s, 700s. You'll notice here our unit was 750 and we're seeing like 700. Um, closer to 700 here. And you might be wondering why I'm keeping these, and they're sort of referring to them as their actual data when you probably expect them not to be. That's because the flipper's accuracy is within about that 50, so it's going to be give or take. So that what the bin raws do is they take all the values and then they kind of average it. This read raws will just give you whatever values there were, and it obviously misses. It misses a ton, and it can miss by about 50 or so, give or take. So this is within 50 of 750, so we're keeping that. Often you'll see, if you've looked at Flipper protocols before, you'll see a TE delta of say 100 or 200, and that's basically 100 microseconds or 200 microseconds, give or take. So it's a good rule of thumb to sort of 100 microseconds, give or take, would still be a valid data bit. So this is certainly within that, so it's a valid data bit. This is within that, this is valid data bit. Just doing go through. Here's one that certainly wouldn't be. It's certainly different to the rest. Probably wouldn't be valid. Could also be a large a large set of zeros. It could be basically 750 30 times or something as well. But a good way to find the end of your signal is to find a long bit of silence, or a long bit of a low, of no noise, of no signal, no transmission. And that's what this is here. And you notice straight after it, that value is not within spec. This value is also not within spec. This is about 100 out of spec, or 200 out of spec. That's not in spec, that's not in spec, that's not in spec. So that right there looks like the end of our signal. I mean, I could even just say this is not in spec here either, so that can piss that off. That's also not in spec. This isn't in spec as well, but because we don't want to, we sort of want to hold on to this one because at the very beginning there's always going to be some noise and a signal and a part of our signal sort of mashed in together. So we're just going to keep this one because we could have a bit of information inside of this noise here. So we'll hold on to that. And if you remember from the bin raws, we had all those sixes, which is 0, 1, 1, 0. Oh, this is actually a 0. Yes, um, oh, that's a yeah. Hmm. Got the 90 on it. Hmm. That still actually works out. No, that's fine. I just had to stare at that for a minute. Um, Now let's get on to this one. So we're back into noise here. So we should find our signal and go backwards. That's within about 100 or so. So that's still pretty decent. This is way out of spec, so that's going to be noise there. Um, and yeah. As we can see, um, that's our that's six. That's zero. So 0, 1, 1, and then 0 again, and then it goes into 0, 1, 1. Yeah. So that's our start of data there. This is still technically the same. It's just this might actually be 1, 0 with a bit of noise in it as well. So it's probably coincidence that it's come to about this 15 mark, this higher 15. But you don't really see so much of high 15s here. So yeah, this might actually have a bit of this one might actually have a bit of noise in it. Might just be a singular. Um, we'll try and find that really long value that's got something that makes sense behind it and something that makes sense, something that doesn't make sense in front of it. So there we go, that's two signals there. Um, Continue pulling this apart. Oh yeah, that's the 7. Oh, that's a really good one then. Yeah, this is all we can just don't even have to keep any noise for that one. That one's bloody perfect. So is this one. This one's actually quite good too. Yeah, that's it there. Where's the end of this one? Oh, hang on, we should do the front first. Minus, yeah, that's still good. So I'll grab from about here, and then find the end. Shoot, is that here? No, that's not it. Ah, here it is. Here, grab that noisy bit, get rid of the rest of the noise. Yeah, that's actually good. Yeah, that's fine. Ah, and the rest of that is just noise. Okay. Right, so now what we've managed to do is we've managed to isolate each of our signals. So if we wanted to just send well, what we could do actually from here is Control C, paste that here, go back to our raw here, grab that, copy, put that back at the top here, and then grab these. We don't have to actually, we could just back all these up together and just do it all as one, but if we wanted to sort of still have a bit of a visualization, if we were to look at the file again, we can add that raw data thing again if we wanted to. The .sub files let us do that, just like the bin raws did. Like I said, we don't have to keep track of anything. So we can do, oops, we can do this. Then we could save that the same way. Make sure to call it, make sure to select all files so you don't save it as a .text again. And yeah, we could send this out. So now we've got our signals being sent out without all that noise in front and behind it. And just nice and isolated our signals. We just put them back in and send those out. We could choose to only send let's see. If we wanted to, we could make a file for each one. So say for example for this one we only wanted to send this last one, we could cut all of these out and just send that one, and then maybe with the other ones, hold on to them and make dot sub files out of each of these ones. Um, yeah, so now we're able to just send one without any of the noise in front of it or any of the noise sort of behind it. The reason you might want to do this is if you're using, say, the Subscript Kurtz remote app. And when you recorded your signal, you've got a ton of noise in front and then the signal. So when you use the remote app, you press your button and then you wait and then it happens. And then you're waiting for it to end as well, so you press another button. If you do it like this before you make your remote, it'll send the signal immediately. And as soon as the signal's over, it's over. You can even remove these silence bits here as well. In the case of frequency shift keying, if there is a Control Z, if there is a bunch of data at the end, empty data, sort of lows or zeros at the end, you want to make sure that you leave them there, because with frequency modulation, the zeros are the ones that actually transmitted information. So the lows might actually be important, but with on-off keying, the lows at the end go on to infinity technically, so they're less important. If you're using like subdecode or some of the decoder, there's subfile decoders and stuff, they like to see a bit of empty space at the end, uh, or like to see the zeros, the lows at the end. So you'd want to keep this, so that way they're able to decode it. Also, if you're sending multiple back to back, you want to make sure you keep a bit of a gap as well. You notice when you hold your remote, you'll have sort of the same amount of gap between each one. That's the gap that you'd want to use. That same duration of gap. So if you're doing, say, like a brute forcing thing or something like that, or you're sending a bunch of signals back to back to back to back, you'd want to make sure you'd keep that gap. Some signals, they don't care if they're back to back to back, so you can remove the gap, but usually they want to have a bit of a wait period between each signal. So that's just something you can kind of experiment with. Now, so what have we done so far? We've managed to isolate a signal now from all its noise. What if we wanted to clean up the noise that's actually within a signal? So let's do that. Let's grab this data here, paste that there, and let's start pulling apart some of the noise that we find inside of a signal. So what we see here is we see about 1500 on average, and we see about sort of, round to that nearest 50, give or take. We see, yeah, we see it's about 750, around about 750 on average. This one looks like a good one. So we're going to want to clean that up, and this one I might even clean up as well and make this 100,000 zeros in there. And this is going to be a 750. Let's copy that and turn all these 700-ish numbers into 750. Make them nice and clean and round. And what this will do is this will sharpen our signal up. So maybe the receiver was having a bit of trouble receiving it, and the reason could be that the signal was just wasn't very clean. It was a little bit noisy, a bit messy, not quite good enough for the receiver to understand it. So we would do something like this. We would clean that signal up. You could do this with like a Python script or something like that. Don't try and get the AI to do it though. It usually will mess up all kinds of shit. You'll wind up with data that you never even gave it in the first place, and nothing will ever work. Also remember that one up there. This one's a bit too far out of spec. That's noise, so I'll get rid of that. So hopefully I just got all of those. So now I'll do these 1500s as well, and round them up, round them off. Um, yeah, I could just go ahead and skip all this, but I can sometimes confuse people when you're trying to understand something, and then all of a sudden they skip the video ahead um, by bloody 10 minutes, and you're stuck wondering, well, hang on a minute, what did they just do? What did they just change? And why did they even change that? Or what just happened? I like to do it this way, sort of right in front of your eyes, so that way you can really get a sense of exactly what it is and why it is that we're doing changing these values, or whatever part of the process we may be up to. There's it's less jarring, you know. Oop, Jesus. Sure. Really post that in. This does take a minute to do, but I don't know, I find it pretty relaxing just to kind of sit here and mindlessly play with some data. But yeah, I usually use a Python script to do this. I sort of give it the parameters, and then it goes and finds all the values that are close to each of the parameters, and it just spits back out the file for me. But obviously, without knowing how to do it by hand, it's a bit difficult to make that leap and start using a tool to do it for you, because then you're a bit, you get a bit confused of what the tool even did, how did the data change, what happened, what am I even finessing here. Yeah, almost. Oh, that one's already good. Oops, so was that one wrong? That just takes a while. Luckily, I'm only going to do this for this signal. There's no way I'm doing it for all of those other four, so we don't have to sit through that. Looks like I've got them all. Yeah, looks like I've got them all. Right, so now we've got a nice, clean, pretty looking data now. So I'll just grab this, and we can save this as our .sub file now and send that out. We've got a isolated signal. It's isolated from the noise, and all the noise inside the signal is cleaned up. So this is just an absolutely perfect, pristine signal ready to send out. And also what we can do is, now that it's really nicely cleaned up, is we can actually go ahead and start pulling some of the data out of it, just like we did with the bin raw file. So I'll just turn all of these, do the minus ones first, all of these minus 1500s into two zeros, because it's a double. Replace all. Turn all the positive 1500s into two ones. It's a double. Replace all. Then turn all of these minus 750s, each, into a single low or a zero. Replace all. And then the positive 750s into a single high, or just a single one. Replace all. And then here we've got just a bunch of zeros, so I'll just throw in a bunch of zeros here, and remove that spacing as well. And there we go. Now we've got that binary again that we originally had with those bin raws, and then we can go ahead and find the find that Manchester pair on it, or work out what our encoding is and stuff like that. That looks like the Manchester pairs, and then find where our data was. In this case, because we've already done it, I'm just going to go ahead and do that. So that's that 1010, that double thing, and then everything else before that's that preamble, that alternating preamble. I don't need these zeros here, so they can go. Copy that, paste this here, and then I can go and de-Manchesterify that data, like so. And then we break that up into its hexadecimal middles. So 4 bits makes one hexadecimal value. And now we've got that what was it? What's that? It's B445 CC ODO1. That's I did press one, did, but I pressed something else there. One, what's that? B61E. And I can compare that. So if we can find that oh, here it is, to that other one. There it is there, look. The same kind of, yeah, the information is very identical. Yeah, there's only a couple of spots that it changed. Here, and here. Obviously, if you look at my previous video, you'll know you'll get to learn about this protocol and what parts change and when they change and why they change, how they change, etc. Yeah, it's a good indication, that we've decoded our data correctly again. So now we could obviously, if we wanted to, we could change that information too, right? We could change that E to an A, and then this here turns to an A, and then that's our last. This is Manchester, so we need to go 8 bits here, and make that A, so it's 10 10 10 10. There we are. Then we can put that back inside of our whole transmission here, just so we get rid of this, and then turn that into we're going to turn that back into its pulses now. It's a bit different this time, so we'll turn that into its individual pulses, which may take some time. You can have a script just smash all this out for you, but it's good to do it. Show it by hand, so that way you actually know what you want what you want such a thing to even do. Right? It's good to know how to handle the data yourself before you go ahead and use a tool to handle the data. It makes debugging things later much easier to do because you understand what it should have done. So this is going to take probably another 5 minutes again. So we could have changed, sort of anywhere in the data. We could have changed more than just the last bit of data. We could have changed 5 or 6 bits, or so. We just did change 5 or 6 bits. We changed 4 bits. We could have changed like the whole 30-bit message or something like that. We could have changed sort of whatever portion of it we wanted, and then we could test that against the device and see what happens. Or if we wanted to advance, say, a rolling counter or something, we would change that part of the information, and we'd send that back out, etc. So we're able to actually have a bit of a hypothesis or a bit of a guess at what we think might happen, or what we think is happening, and then we can actually actually test that. So what I'm hoping to sort of accomplish with this video is to give people the tools in order to actually do some real analysis with the flipper, and do more than just replay and capture, to actually be able to pull apart the data, modify the data, send back out modified data, and see if you can, sort of spoof some of your own devices and change up um, uh, um, different things. I mean, maybe you've got, say, like a fan or something that's only got that um, appears to have more than one setting, but you've only got one button. So maybe you could change some button value, and then see all of a sudden that your fan now has a different mode. Um, it's, it's quite actually quite common for things like that to be the case. This gives you the ability to do that, or you want to create a signal from scratch. You have some information written down about a signal or something, and you want to rebuild that back out, so you can build that out. Or you've got some demodulated bits from a software-defined radio, and you want to be able to put them into a .sub file. This is how you would take raw binary and go ahead and put that back into a .sub file. We've already done the bin raw file. This here is how you would go about doing that in just a regular .sub file. So we've broken it up into its little pulses. We have a pulse of 2 and a pulse of 1. Different protocols will have different length pulses, or different signals will have different style pulses. Now, how do I do this? I know that this one's a bit funny, so I can take these 0 zeros, Control H, and turn them into minus 150, 1500s, because they're doubles. But yeah, replace all. Yeah. Why didn't that didn't work? What have I done? Control H. Oh, okay, so minus 1500. Replace all. Oh, I can do the ones too, because there's nowhere else that 1 occurs. That's good. And turn that into that. Okay, into 1500s for the 1s, because they're double. Now, if I want to do that with the zeros, it would unfortunately take each 0 here and turn it and mess me up. So I have to do this one by running in minus. That was a 0, wasn't it? Which was yeah. So minus 750. Now I just copy that. Copy it. Then go through and find all the zeros here and turn them into minus 750 is just a single zeros. There's one there. There we are, and then the ones will just be positive 750, so I'll just copy that. And why not? We'll go backwards for these. Change the ones over. Literally just double clicking and pressing Control V to paste. If anyone was wondering. And oh, I missed a zero. There we are. And we can add our minus well, 100 or 1,000 at the end as well. I'll copy that. No. Do it the other way. Copy that. Oop. So that's the original data, and this is our modified data. Now we could save that and then send out our modified data. We can also go ahead and well, we can just get rid of all of it, right? And send our own data. So back on that ASCII thing, we wanted to send hello. We would find out what the ASCII is for hello. Say it's whatever the heck this is, for example. We'll pick a time unit for it. Let's say we want our time unit for this to be 500. So now we'll go and break it up into its pulses, like so. That's actually good. That's a pulse there. Yep, that's also. Whoop, 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 whoop. Okay, so we're separating the zeros from the ones essentially into their pulses, and now we see so that's one positive. That's yeah, the time unit is just 500, so that's correct there. This would be three 500s negative, so that's minus 1500. Then we've got two ones, so that's 500 times two, so that's oh Jesus Christ, that's 1000. Is it? Oh wait, where am I? I've lost myself. Hang on. We've got positive, three negative, double positive, which is 1000. Yep, and then yep, minus 500, and then 500 there, and then yeah, minus 1000 for two. And then there's a positive 1500 here. Then there's a minus 500. There's a single unit. There's two unit. That's 1000 positive. Oh wow, this is really hard to see. Yeah, I'm just going to try to space these. Kind of space these out to match my really difficult to bloody see here. Right, so that's where I'm up to. So that's a minus 500. We got too much space here. Then we're going to have a 1000 positive. And here we've got negative 1000 because it's two 500s. If this is too confusing, what you actually can do if you wanted to is you could just put positive 500, positive 500, positive 500 and just do it that way. It would still work. You don't actually have to bunch them all together, but it's cleaner to do it that way. Actually, you'll probably find that when I did the end here, oh no, that's good. Okay, so that happens to be a negative. But if this was a positive, it would have been invalid anyway because it wouldn't have been a Manchester pair. Wait, no, wait. 1, 2, 3, 4, 5, 6, 7. Yeah, 8. Yeah, okay, yeah. So yeah, if this was a negative here, we would just bunch it together and make a negative 1500. But we were good here. But you also you don't have to if you wanted to make it a little bit less confusing for yourself. That's a positive 1000. That's a negative 500, and that's also a positive 500 there. So it's just a 500. Right. So yeah, you can just piss that off. Literally just put in your own data like that. We gave it our own time unit as well, and there you go. There's our own sort of synthetic data. If maybe we wanted to make our own protocol or something for communications, or we were using a microcontroller project or something like that, and maybe we wanted to communicate a command to it, and we used ASCII over radio to do that, or we wanted to send the commands a command to it of let's say 3, so you would literally just send 3 in binary to it, which would wind up being at this time unit of 500 would just be one. That would be minus 1000, and then that's positive 1000. You can also encode it the same thing if you using that time unit of 500 still. If you want to make it a little bit less confusing, maybe you will actually be able to do minus 500. I put a space there. Minus 500 minus 500 uh, positive 500 positive 500. You can actually still get away with doing this, and it's completely fine. Um, this is obviously a lot more cleaner, and I'm not sure if this can hinder the accuracy of the transmission or not. I'm not even really. Oh, I suppose I could test that if I wanted to, but I never have really looked at that. But it is doable, and it does work. Um, so yeah, you could do that, or you can just kind of keep your pulses nice and clean like this. But that's how that's how dot sub file the raw dot sub files actually work. That's how they store information. That's how they transmit information, and that's how you can you can pull information out. You can mess around with it. You can put your own information in. You can create your own. So basically, what we did there from the start was we had a bunch of we recorded a signal, and then we isolated that signal. Removed all the noise from before and after it. We then we just sort of grabbed a single signal, like oh my god, a single isolated signal, and then we went and cleaned that signal up, make it all nice and neat and tidy. We then went and changed some of the information in it, as you can see. We altered the information in our is that the only thing that changed? Right, okay. We altered some of the information in our .sub file, and save and retransmit that, or we can also have a way of building our own. So you literally just type this out, this bit, this bit, this bit, this bit, and then just add whatever raw data. Obviously, a good way of doing it is just sort of picking the modulation and frequency that you want to use. And this was just I literally just recorded nothing and hit save, and then saved that as FM. And then I could literally just remove this and then put in my own information. And when I opened up the file, or whatever, I could have, or maybe take information I already have and put it over into it. No, that's not the file that I just opened. Um, just replace it with that, and then save that and retransmit it back out or whatever. But, yeah, there's actually no signal in this at all, and you can see that immediately. But this is just actually, maybe I did catch something actually. So no, maybe not. It kind of looks like maybe I did. Uh, that's funny. Um, anyway, yeah. Okay, where's there it is? That's where we're up to. So I might cover everything. I just want to make sure I covered everything there. Um, we looked at the bin raw files. We looked at extracting information from them. We also looked at how you can change information and retransmit that. We looked at how you can make your own bin raw files with your own information. We looked at how you could do the same things for a regular .sub file. We looked at how you can find a signal in a .sub file, isolate that signal, clean it up, make it nice and sharp, change the information that's in it, and retransmit that. No, we looked at extracting the information out of it, decoding the signal, and then changing the information, turning it back into a .sub file, or back into that, um, turning it back into a .sub file format to retransmit back out. And we also looked at making our own data for a .sub file, or just a regular .sub file as well. Um, good, good. That covers everything. Um, in the next one, I'm probably going to do get back to the row and code car, reverse engineering thing that we've been doing. So if you're interested in that, definitely have a look. The previous video goes for a really long time, but it's just chock a block full of information, and it's also the entire process, like just live. So if you're interested in that kind of a thing, give that a watch or whatever. Um, and yeah, in the next video, I'm going to sort of continue on by essentially doing the same thing by recording a signal, changing some of the data, sort of decoding it, and then changing some of our data fields to what we think's happening, and then literally rebuilding that back out, putting it into a .sub file, and then transmitting that to the vehicle, and seeing if what we have discovered is in fact true, and see what happens. See if we get it or not. So that's going to be pretty exciting. But I had to sort of cover this stuff first, so you could sort of understand what I'm doing in the next one. I also get this question a ton about like how someone would go about analyzing a analyzing a signal that's not a supported protocol, and like what all the data in a .sub file actually is, and sort of how to do some of this more advanced stuff. And the information I've given you in this video here is going to give you like those raw basics in order to just take it and run with it. So it's just now that you know how to make a signal and pull apart a signal and change a signal, the limits, your imagination really. Yeah, so I think I might just leave that there, I guess, and see you all in the next one. Peace out.